Okay, hello everyone. We're going to talk about PyTorch XLA today. I'm Han, and I'm a software engineer in PyTorch XLA team. I'm here since 2023, so roughly 2 years. Before that, I was at Meta at PyTorch compilers, also similar stuff. Fun fact about me or about my previous job is that our team used to own Torch script, and we deprecated Torch script. The announcement is still not out yet after 2 years, but yes, it's deprecated. Nobody's working on Torch scripts. Yeah, so I'm gonna talk about Torch XLA. The plan of today is first we'll do a recap of history, both from the PyTorch history as well as the PyTorch XLA history. I'm gonna walk through some of the new features from the 2.7 release, which happened in May 13th, and then highlight some sister projects and do some future-looking discussions. And we are a small group, and it's going to be interactive, so feel free to ask questions anytime. I have the last time we actually run over a little bit because a lot of people ask questions, but don't worry about that. The content is flexible, and also I don't have a exhaustive list of everything we're going to do for the future, nor everything that's in Torch 2.7. I'll talk the parts which I'm familiar with, most familiar with, and then talk a little bit less about things which I'm. A quick slide recap on PyTorch XLA, like the entire stack. PyTorch is here, and PyTorch XLA is a layer here. To run anything on TPU, we have to use the OpenXLA stack, which means that given a PyTorch program, we want to capture the operators as we go, and then create a corresponding XLA graph and run that through the XLA ecosystem. And this is the same runtime that JAX uses. Even also TensorFlow, even though people don't talk TensorFlow that much, but yeah, TensorFlow also goes through the XLA stack. And then if we look at PyTorch, the project itself, we're gonna say two things. One is all the Python code, Torch.nn modules, and things that manipulate tensors, optimizers, all those things written in Python. And then there is a C++ component where all the operator implementations, both in C++ for CPU as well as in CUDA for GPU, are implemented. And then the Python part will just forwardly call to wire them up, right? To call the C++ parts, right? So for Torch XLA, we are actually replacing the C++ part in some sense. We are registering our own callbacks for operators, so that up to every run of the operator, we're running our version of the PyTorch operator on XLA instead of the CUDA one, because TPU doesn't run CUDA. Right? So that's roughly how the entire system works. And then the upstream, right? So Hugging Face or PyTorch Lightning that interacts with PyTorch through their Python API is supposed to run also on PyTorch XLA automatically. In practice, not so true because people over-optimize stuff, and also a personal rule for myself is that things that should run theoretically, if I haven't run myself, I will not claim that it runs. And certainly, I haven't tried it to run all of the Hugging Face models on Torch XLA. Some of them runs pretty well, but not all of them. So yeah, going a little bit of history of this project, it started 2018, and with Meta, together we are building a PyTorch backend for TPUs. And at that time, PyTorch itself is actually much smaller, right? PyTorch roots traces all the way to 2001, I believe, in a project called Torch. And that project is a C++ library mainly of operators with a Lua binding. So it's also called Lua Torch. Some people might remember that. And Andrew Karpati wrote the first version of like character RNNs on Lua Torch, and it's actually pretty good. It's pretty performant. But then around after around I think 2007-ish, Meta realized that keep betting on Lua is probably not a good idea. So they decided to make a Python bindings to the Lua library. Then the birth of PyTorch. One thing they did remarkably is that it's not merely a Python binding to a C++ library. Instead, it's a Python first library, right? They first design the Python APIs, and then they say what part of Torch I can take over and port over. so that it feels like you are writing Python. You're not writing like C++ using Python syntax. You're actually writing Python. So that's a feel that PyTorch these people made in the very beginning. They're a tiny team. I think they started with 5 people. And the mantra that when I used to be at Meta, the mantra that people say is PyVidia, like parallel to Wintel or Windows, right? So it's a um, yeah, it's a funny time where they better to say okay Python first, right? Unlike TensorFlow one. So yeah, and that did great as a pretty good decision, and then its usability and ease of use made it to grow. And in 2018, I think PyTorch is actually much smaller than today, and then they are trying to be multi-backend at that time, and we started the project collaborating with Meta. And then it's based on this lazy tensor API, and the reason is because XLA, even today, want bigger graph. The bigger the graph you give to XLA, the more room you have to optimize and to like do buffer aliasing and do fusions and stuff and whatnot. So people want to give bigger graphs to XLA, and that's the reason why we made this lazy tensor approach, which we'll go into more detail in the later slides. But and then in 2021, when we're still like adding support to different models on different TPUs, the work which we did before I was here actually is support more models, support more customers, and support more TPUs and PIs. Around 2021 here, something happened at Meta, which is Torch 2.0, right? The Torch 2.0 integration with OpenXLA comes 2 years later, but 2021, end of 2021, they announced the Torch compile and Dynamo, and I was at Meta at that point, and there used to be 2 parallel teams, both fairly small, 3 people each, I think. One working on the lazy tensor stack, which is supposed to be how a backend that needs a compiler should integrate with PyTorch, and one is working with Torch compile / Dynamo, which is yet another way of how a backend with compiler is supposed to integrate with PyTorch. And then there was this meeting when the 2 sides are presenting their data, and they try to pick one, and they pick Dynamo, right? And the story is that okay, so lazy tensor, instead of being a generic backend that everybody can hook into, becomes the only backend used by XLA, right? So XLA right now is the only backend that's on lazy tensor, nobody else. Everybody just integrate with Dynamo themselves. And then we also pivoted from here. So we also launched a 2.0 Dynamo integration with OpenXLA. It still uses lazy tensor, the C++ class, because our lower rings are written against those classes. You have to pass the objects of the right type for it to compile. But beyond that, it's actually don't use the laziness of lazy tensor that much, right? You just use the lazy tensor as a tracer. You trace it with the lazy tensor again after you get the graph from Dynamo, and then you do the lowering that way. And it's actually the PyTorch 2.0 is actually quite remarkable in the sense that you nest Torch compile and then lazy tensor and then HLO. You do the more nesting, right? But you get faster execution, right? You hit the Dynamo cache more often than you hit the lazy tensor cache, and then you don't compile and you don't even retrace. You just hit the cache and you get a callable. So it's quite remarkable that even though you're nesting more layers, you get a faster executable. So that's great. And so we have this. If you do today torch.compile with backend equals OpenXLA, that's the experience you're getting. And then the timeline continued. 2024, last year, we did JetStream PyTorch. That's an inference solution. JetStream was released as an inference solution for JAX. And we added a PyTorch backend for it. So we also have an inference solution for PyTorch. This work was announced last year in Cloud Next, and now is the current plan for it is to merge into VLM's JAX support. We started TorchX as an experimental feature inside of Torch XLA. We started working with Llama 3. We got pretty good performance on Llama 3 in 2 parts of V6E. We got around like 35% of MFU. one of the features we leverage is a scan, right? Scan is a feature where, if you have a neural network that happens to be one block, one module, and repeat a lot of times, like Llama, you have the attention plus FN module repeated 32 times. You can use scan to make your graph smaller, right? So if you do the regular trace, you will have a very big graph. You basically flatten the entire neural network into a flat graph. Your graph is very big, and the compile time will suffer a lot, right? So if you compile Llama 4.5b, which is a big model, you can get up to 40 minutes to an hour waiting for the first compile. And if you do scan, then the size of the graph will shrink because you have one layer and then a while loop around that layer. So the number of nodes on your graph is much smaller. And the complexity of compilation is actually super linear, right? It's not linear in terms of node. It's at least quadratic because of the pattern matching stuff. It could be worse. I don't know top of my mind what the complexity of XLA compiler in terms of number of nodes. But we can do the measurements. It's not linear basically. So here we can save a bit compile time. You actually could actually get a slower graph runtime because XLA will not do fusions across layers. But which is fine. JAX do this. JAX.lax.scan do exactly this, and we implemented this scan for Torch XLA. Question.
So why does XLA for JAX at least does fuse across layers?
If you do JAX.lax.scan, it doesn't.
Oh, it's scanning.
Yeah.
But there is so when you use Dynamo with PyTorch and PyTorch XLA, you pretty much dispatch the whole graph to XLA, or do you split it up into graphs?
Usually, so Dynamo decides when to split the graph, and we get full graphs. We get graphs from Dynamo, and we don't know whether that's a full graph or not. In practice, if you do training, you will get 3 graphs. You get the forward, backward, and optimizer step as a separate graphs. If you do inference and your model don't have anything that triggers graph breaks, then you should get one full graph. There is a mode of full graph equals true that Dynamo will give you error if it cannot capture it in full graph. Yeah. Yes.
So for the Torch X,
yes.
Is this already publicly released?
Yes. Right now it's alpha. So it's experimental in 2024. Here in beginning of this year is alpha. Alpha meaning the API can change, and but it runs. Yeah, it's already the source code is inside of PyTorch XLA same tree. And as of today, if you install PyTorch XLA 90, you get Torch X also in the same wheel. Yeah.
And what does it mean for the V60 support specifically?
V60 is a version of TPU which we just released. V60 support just means that we tested V60 and we did the performance benchmarking to make sure that it doesn't have regression and whatnot. For Llama 3, 4, 5B on V60 2 paths is 35%. Yeah. So that's 2 paths. The network between those 2 paths are data center network. So it's a multi-slice training. Yeah. Okay. And
I have a question. So
yes.
For JAX, for example,
yes.
PyTorch, you already said that for training, you can get 3 graphs, forward, backward, and optimizer.
Yes.
Right? For JAX also, do I like a similar sort of graph, or will they fundamentally be different if I log that out in a profiler?
Yeah.
Will the graphs be fundamentally different, or they have similar?
For JAX, okay, so JAX philosophy is more explicit. Basically, like you have Python functions, and then you decorate the Python function with JAX.jet, right?
Yeah.
So whatever you decorate as a JAX.jet, that's the graph you're getting, right? So if you read def train step and you put the entire train step inside that graph, you do JAX.jet on that graph, you get one graph. The one graph with both, forward, backward, and optimized. You get one graph, right? If you want to get 3 graphs, then you would put the forward as one function, and you do JAX.jet, and then you put backward as one function, put JAX.jet, and then you wire it up outside of a JAX.jet environment in Python, then you get 3. So it's your option, your choice, and they are very explicit to say, okay, whatever you decorate on the function will be one graph. If JAX fails to trace that into one graph, if there's a either data dependent control flows or something that picks into the tensor or some globals or whatever that JAX doesn't like, it will give you exception right there. So you basically, if you succeed, it give you one graph. If you don't succeed, you get exception. PyTorch, on the other hand, Torch Dynamo's design philosophy is to be eager compatible, right? So their philosophy is to say, okay, if I cannot get one graph, I'll fall back to Python, let Python do the Python thing, and then I'll come back. So there's a little bit of design philosophy differences there. Yeah. Okay. Okay. So right now we are here, H1. We're just ending H1. We're starting to do eager mode exploration. What that means is that, lazy tensor is lazy, right? So you are only getting the values as we go. Eager mode, we want to get the PyTorch and GPU experience, right? So the North Star is really, why should PyTorch on TPU be that different from PyTorch on GPU, right? Ideally, you just want to say device equals XLA or device equals CPU, device equals whatever. And you change that, and you don't change anything else, right? And then you are the same PyTorch program that runs on GPU should run on TPU. That is really the North Star that we're aiming. And that's why we're starting this eager mode exploration. And in the future, we hopefully to graduate this exploration to a feature in the future. Usability improvements, documentation, error messages, making sure that whatever error message that XLA throws at us, we properly handle them and present them as a Python exception instead of a C++ stack trace. D-tensor integration, so this is a feature by PyTorch that wraps the PyTorch distributed local view to a global view with D-tensor. So this actually resembles what the SPMD way of programming with the mesh and like axis-based sharding. So it's very natural that for us to support that way of the paradigm by implementing D-tensor APIs using SPMD so that we can also participate in this API. There's a JAX bridge, meaning we can call a JAX function from PyTorch XLA, which later on I'll do a deep dive on this because I happen to be more familiar. And TorchX from experimental reached to alpha stage, meaning the operator coverage is more complete. We have 95 plus operator coverage. Most of models can be traced with TorchX as well. It's alpha, meaning API can change. If you look at the TorchX code today, you will still see a lot of JAX like exposed to a user, right? So we want to do some UI work to make sure that even though it's implemented in JAX, you get a PyTorch feel out of it. And we know it's possible because we did it for PyTorch XLA, right? When you are using PyTorch XLA, you don't feel you are writing XLA builder. You feel like you are using PyTorch, right? So this is the same thing we want to do for TorchX. Question. Eager mode, yes.
So what advantage does it bring other than similar behavior to TPUs and GPUs?
Yeah, for customers, the value proposition is that customers need to change less code in order to make it run on TPU. So there's a friction of, I have this model running on GPU just fine. Can I come to TPU? And then the answer that we gave them right now is not very a good answer. Is that depends. You have to try it. It might be very easy, might be very hard, depending on your model architecture. Because XLA, lazy tensor, if there's too many graph breaks, you get a horrible experience, and you get random errors. So the eager mode is really a kind of like an improvement on the UX to say, okay, it will run out of box, and the performance is gonna be okay. We don't promise to say top of the line, 50 plus MFU out of the box, but at least it will run, and then you can profile from there. You can put more things in compile, and we will also have a Dynamo backend, Torch compile integration. We already have one, so the more things you put in Torch compile, the better it performs. Same with GPU. In GPU, it's also gradual compilation where people have eager mode. They can opt into Torch compile for some layers, and they can have custom kernel for other layers, right? Things like that. So the same experience that GPU people having, we want to give them to the TPU customers as well.
Isn't also some benefit of eager mode, like rapid experimentation?
Yes.
If you have like some huge model that takes like an hour to compile, with eager mode, you could run it for a few steps.
Exactly.
Yeah.
Yep. And one thing which which I think the eager mode adds is also debuggability, right? You put the PDB breakpoint, you stop there, you can inspect the shapes and the values and whatnot. In lazy tensor, you still can, but guess what? The moment you print the tensor, you actually introduce a new graph break. So whatever you just debugged in the PDB is not the same thing that if you run it again, right? And that's kind of defeat the purpose of debugging, right? So there's a lot of things that eager mode gives in expense of performance. But and I think a lot of success of PyTorch is on the eager mode, right? Like TensorFlow used to be the market dominant, and where did it lose? It lose on the UX. So it's then we also want to be like closer to the PyTorch ecosystem as possible. And today the Robert's talk, these are also feedback that we received from PyTorch core maintainers and Meta to say, okay, you really want a good PyTorch experience on TPU, you have to do eager mode, you have to do compiler integration the way that we expect you to do, and that's the dynamo backend, and then you have to do a distributed API which is familiar to all the PyTorch users, right? If you do GSPMD, fine, but if people can only use GSPMD on TPU, on XLA, then that looks very different than what they get from elsewhere. So do go through the same API so that the user don't have the jaggedness, which are very fair points made. Questions so far? Okay. Yeah.
So I'm working on very
Mhm.
because I'm moving from, let's say, Conda to Astral a lot, and so I want to figure out what are the wheels which will be compliant with JAX, PyTorch, XLA, like combined, so that there's not a mismatch of all the different versions, because a lot of them are different versions. So is there like any in Google, like is there a policy of maintaining compatibility across all of the?
You're moving from what?
Like from Conda to Astral. So I just want to try to figure
Conda to SRAM.
Astral. Yeah.
Okay.
UV basically. So I'm trying to understand if
UV, yeah.
Yeah. Basically, is there some wheels which you guys have prepared which will be compatible with all of them? Because right now there's a lot of mismatch across, like what PyTorch needs for QDNN is not exactly what JAX will need for specific QDNN, QDNN.
I see.
This is like
very good question. Yes. So in cloud, we have this project called Stable Stack. Basically, is what you describe is and also beyond just frameworks, also what version of the data loader you are using, what version of. So they say, okay, let's pick a opinionated set of libraries, and they run a bunch of tests to say, okay, they're compatible with each other. However, right now, I think the current stable stack, they're releasing Dockers. They're not releasing like
That's fine. I can use Docker file.
they're releasing Dockers, and also right now it's TPU only. So the GPU, the GPU stuff is missing. Yeah, but I think that's a good feedback, and yeah, it is a good feedback. I'll give it to the GPU people or stable stack. Yeah. Okay, so where we're going for future, and I'll be very honest. There's a lot of unknowns to the future on how the thing's gonna be implemented, because we need to experiment, right? And one of the reasons is that, okay, there's so many ways you can go from PyTorch ops to stable HLO / XLA to run on TPUs. Now with Palace in the mix, is also valid option to emit Palace. So there's so many ways to do it. But the direction which we know for sure is that this is the line we want. Be more PyTorch native, right? Be just like PyTorch on GPU. That's where we're going in the future, and that includes eager mode and improved dynamo backend, right? So the current OpenXLA backend, is compliant, it's valid, but then we also want to say, if we want to make it better, sorry, how should it be? And then they're gonna be 2 experimental features. This is more to support the newest TPU Ironwood, which is announced. FP8 native FP8 support and Sparse Core support. The FP8 support today, even you have the data type, you can represent it. The math is not done with FP8 hardware units, because there's no FP8 hardware unit in the current version of TPU. So for the future, we want to emit the instructions so that it utilizes the native fast hardware unit for FP8. Yeah, so this is a rough timeline in comments so far.
I have a question.
Yes.
Related to the TensorFlow backend.
Mm-hmm.
I remember like TensorFlow took on also like trying to get the eager mode, but that increased the really like the gap for the
Yeah.
customers. And so what do you think on this one?
Yeah, that's a very sharp question, and thanks for that. I remember that. TF1 to TF2 migration was not a well done one, and the reason is because you deprecate something and then you don't your replacement wasn't fully a replacement, right? So people on TF1 it's very hard for them to migrate. They have to do a lot of rewrites to get TF2, right? And that amount of rewrites they could just rewrite in PyTorch, right? Why would you rewrite in TF2 if you can just rewrite in PyTorch, right? So and then the new users of TF2 also, it didn't give them like that much more compiling reasons to come to TF2. So it wasn't a good idea. I would argue it's more on the execution than the idea itself, right? So eager mode, there's many ways to do eager mode, and the details is how we execute it. And here we actually don't we are only starting, so we haven't done that. But having learned the lessons of TF1 to TF2, I hope we can do a better job. So for example, we can make a release with eager mode bundled where you can enable and disable, right? Default is disabled. You can try it first, right? And then when you enable it, your code still run. You just have different performance characteristics, right? Instead of turtle thing gonna become no op, and then your op gonna run right away. So all your code gonna run, except it's could be slower, right? As what you would expect. And then you slap the turtle compile around your critical section, and then you start gaining speed. And maybe you don't even to torch compile everything. You torch compile 80% of your code, you are back to the same speed, and then we can start iterating on new features, leveraging JAX, leveraging all the things, direct palace, right? Some ops we can replace the XLA builder implementation with the palace kernel that do the op, and then we're gonna repop the benefits, right? So if we do it right, there is a path of there is a path of not have the return of TF2. And let's look back on another upgrade of PyTorch 1 to PyTorch 2, right? And their shift is actually the opposite, right? They started with eager only, and the new thing which added is a compile mode, right? But how the compile mode is introduced is that it's not forcing to say you must go to compile everything, right? It is a function, it's a decorator that you can choose to add part of your code and then interrupts with whatever you had before, right? So that I think we have a lot to learn from what they did there, and try to do the same thing.
The eager mode lowering, is that any different than how you compile code with lore, or is it pretty similar today? It's just a smaller binary.
Today is the same. Today is pretty similar, but to be explored was the best way to do compiled. As Robert hinted, Meta gave us 3 suggestions. 1, do the eager mode. 2, do the distributed. And 3, dynamo integration with inductor, right? Whether we should integrate with the inductor is actually up to us, right? But personally, I think it's a good idea to try it anyways, because if we decide not to go that path, we probably should give Sumit the answer, hey, we took your suggestion seriously. Here we tried it. For ABC reason, it doesn't work out. And here's the report. And we decided on that. And are you okay with it, right? So that's how a transparent collaboration should be. Yes.
PyTorch running on GPU, why don't you guys consider Onyx? Because if I'm exporting most of my models in Onyx,
yes,
why can't you just read the Onyx? Because that's also linked to Dynamo, right? First Dynamo.
Yes.
So can't you just parse that instead of, because even if you make it eager mode, I still have to make some changes, not everything, but some changes. And if your North Star is just to take everything performance based in PyTorch and ship it from GPU to CPU the same way.
Yeah.
Why isn't there a Onyx runtime for JAX or something, which will just basically copy everything in PyTorch into a JAX model completely?
Okay, there's a lot of pieces in this question, so let me parse it slowly. The first is that why don't we consider using Onyx as the intermediate format? Yeah. The answer is that we considered stable HLO to be the intermediate format. So stable HLO for PyTorch XLA and JAX is what Onyx for PyTorch in some sense.
Okay.
And I do have the story for Onyx, which is the idea is great.
Yeah.
The execution have issues, and that's why Onyx is not widely adopted outside of Microsoft. And well, and partially like like the story, the original story is this, because Meta also have Cafe 2, right? And in production they actually still have Cafe 2 a lot. And there was a push of one migrating Cafe 2 to PyTorch, which didn't go too far because PyTorch wasn't performant for production servings. Cafe 2 is C++ only, right? Your graph and static graph, your graph is defined in a protocol buffer is there, and then it's very easy to optimize. PyTorch is dynamic graph, where you don't even have a graph outside of AutoGuard at that time. You're all eager, and the Python overhead and whatnot. So the migration is very hard because like you are an S team, you do the migration, then you run the A/B test. Just because your service is now like 0.1 milliseconds slower, and now you get like negative 3% on revenue, then you're saying, can I launch that? No, you cannot launch that. Right? Very hard to do that. And I know people worked on that migration. It didn't go too well. And then there's a leadership push to say merge Cafe 2 and PyTorch. And that's actually the birth of Onyx. So the original thought was, oh, Cafe 2 production, PyTorch for research. The goal of merging is faster research to production, right? So therefore, what we want, they made an intermediate format where you can export to Onyx, and then Cafe 2 consumes the Onyx. Then you have faster research to production. It's like a great idea. And then Meta started working on that, and then Microsoft joined as a partner. They worked half a year. They launched it. And then their VP says, no, I want you to merge those two frameworks. So like, what the heck are you doing? And then they say, okay, scratch that. And then Meta at that time basically pulled away from the Onyx support. And Microsoft is the only one holding the stick. Not to say the history that will repeat or not, but same thing happened with related tensor, right? So like, but anyways, so Onyx, and then they deprecated Torch script, and Onyx depends a lot on Torch script. So Onyx made Onyx script because they have to have something, right? So Onyx is actually right now not in a good spot. So that's and the stable HLO have a lot of good properties of backward compatibility and stuff, which Onyx also offers. And then there's all the issues with Onyx. Another one is the slowness of adding new operators and version, and they're too strict on the backward compatibility and the versions stuff. Like there's a committee to add new operators, and then adding a new version is pain, and we're moving too fast, basically. Like and we have no choice. The world is moving too fast. Like even I think only for the even for the mobile deployments, like on phones, Onyx used to have an edge on that, but they're starting to losing that edge over like TF Lite, and also losing over XecuTorch from Meta. So the ecosystem on the mobile world is also kind of like split. Like Onyx is one of the players. So like yeah, right now I think only Microsoft is the only serious users of Onyx, in my opinion. But so, and stable HLO, I guess because we are in this OpenXLA Dev Day, we can say, oh, stable HLO rules, right? So that's answer number one. Answer number two is that can you run Onyx on JAX? You can. There is a JAX Onyx runtime, and it runs Onyx op by op with JAX. And if you JAX JIT it, you actually can get a pretty good performance. So if you do have legacy Onyx stuff that like Onyx files lying around and nobody's touching, you don't want to rewrite them, probably you don't even have the source code that's exported that Onyx to begin with, can you still run it on TPU using Onyx JAX runtime? Yes, you can. You can try it. It's actually not too hard to implement. There's a 200-ish ops in Onyx. If you implement all of them in spec using JAX ops, which is a little bit higher level, it's very easy to implement Onyx ops in JAX. And then you have that, and that's what we have done. Not me, not my team, but some of the teams have done that. SS experiment is right now is not much activity happening there, but you really don't need much activity. All the ops are implemented. Does that answer all your questions?
Yeah.
Okay. There was
Yeah. So this may be a detailed question. So if
Yes.
For example, we can use XLA the mark sharding, but however, when we trace the model, actually the either dynamo mark sharding or animal mode in XLA the mark sharding
Mhm.
don't work. What is the recommended way to mark sharding and convert the torch to stable HLO, maybe using XLA API as a bridge?
Okay, so in the final graph, do you want the sharding there or you don't want the sharding?
I want the sharding there.
You want the sharding there, and your question is, when you do dynamo, well, okay, if you and you only want the graph, you don't want to run it.
Yes, I just want to maintain the sharding information in the exploited graph.
Okay, yeah. So for that, what you want to do, for that one, you actually want to use TorchX directly. So you want to do torch export. So let me think. So you want to do, no, you don't even want to do torch export. Yeah.
I think if the final format is torch.export, for example, exported program, that is fine.
No, for this one, you don't want to do torch export because torch export will see the sharding and say, okay, what the heck is this? And will give you errors, right? So the only reason why we wrap mark sharding into the dynamo dot sharding is because otherwise dynamo will say, I don't know what this is, right? But once it becomes a black box, then it will stay there. So what you want to do is you want to write your PyTorch functions with torch access mark sharding, and then you want to trace the whole thing with JAX. So basically, the only tracer is JAX, and JAX knows what is the mark sharding, so you will put the sharding there. I can show you examples afterwards. Okay.
And can I ask
Yeah.
So, I'm not sure if you know that if we want to export QDQ to stable HLO, for example, the stable HLO has uniform quantize and deep quantize, can we just use the native fake quant in PyTorch export torch to stable HLO?
Yes. However, I believe that the PyTorch native quantization will decompose the QDQs into like minus the bias divided. It will give you the patterns, and then like later on you can probably pattern match and then like fold them back.
In this process, I can still use JAX as a bridge. For example, I convert torch to JAX and JAX to stable HLO, and during this process, the QDQ information will still be intact.
Yes, I think so. It will be decomposed, so you don't have a node called DQ, but like the math inline there. Yeah, I haven't tried though, but yeah, I think it should work. Okay, any more questions? How are we doing with time? Sorry, I think I'm going too slow, so I'll accelerate a little bit, but feel free to ask questions anytime. I think having discussion is more valuable than just going the content. Okay, I'll go a little bit faster in this part. So this is the background of how Torch XLA today works. So how it works is that PyTorch implements this vtable called dispatcher table. What it is that it has a bunch of dispatcher keys, and the order is important. So they will, depending on the type of tensor, they will select which kernels to dispatch to, right? So if you have a CUDA tensor, you will go to the CUDA implementation of the op. If you have a CPU tensor, you will go to the CPU version of the op. And XLA there is a hard-coded dispatch key because when we started the project with Meta, they added the dispatch key for us. So every time a XLA tensor goes through the dispatcher with some ops, we will get a callback, and the callback will tell us, here the op, and here's our inputs. Please do your math and tell us what's your output, right? And what do we do when we get that callback? The lazy tensor infra actually don't do anything. It just remembers there's this op that I need to run, right? It's just like when your manager hands you some task, you don't always do it immediately, but you just write a post-it note to say, okay, or put a reminder, right? Then do it later, right? So that's kind of like what they're doing. And the reason is because we want to give bigger graph to XLA. XLA want bigger graphs, right? The bigger the graph, the more room have it for optimization, fusions, and whatnot, right? Plan the buffers better or use less memory and whatnot. And when do we must do the work? For example, training backward paths, printing the tensor, or fall back to a native tensor op, which need to consume the value of the tensor. We will take the node we want to materialize, go backwards, trace all the way to the nodes which already have the values there. We extract the subgraph, we give it to XLA, we lower to XLO, compile and run with XLA runtime, stock XLA runtime. And after that, we will have the values, right? We'll have the value back. And once we have the value, we actually drop this subgraph and write the values into the tensor. So the next time when you print the same tensor, you get the value right away. And next time, if another subgraph that continues from here, we'll stop on the backward tracing. So this behavior is exactly like a future, right? However, the first time you look at it, you're gonna materialize. You're gonna wait and then materialize the value, right? So this is a way to think about it. And as we mentioned, that's a little bit of challenge for using PDB and stuff, because printing stuff actually introduces the graph link.
So then if you're in a loop, is this happening every time? Like
if you're in a loop, you get a longer, right?
And then you come back around again, and now you once again build up the graph, and then
yeah,
compilation cache it.
Yeah, okay. Exactly, right. So in the training loop, the recommendation is that you do torch XLA.sync to cut the graph at the end of the loop. And the reason is that if you don't do that, you will keep tracing, and then next loop will keep tracing, and then in the end you have a huge graph with 1,000, train iterations. And the moment you are saving the checkpoint, you actually like try to materialize all this big ass graph, and then you get OOM, right? So and that's the reason that if you cut the graph on the train step, what you do is that you trace once for the first loop, you run it, and then the next time you trace again. But guess what? Once you trace it, you will find, oh, it's the same graph I just compiled. So you hit the cache, and then you just launch the same graph again.
Because these processes, for example, it's very tricky for me to understand. Is there like a visual representation which you guys can create? Like, this is the graph, this is the cache. If I don't apply this operation, this graph will go this, and create like 1,000 copies of every single iteration.
Yep. Yeah, it's a good idea. We haven't created those animations, but I think it's a good idea. Yeah.
Tutorial for me to see where am I facing the error.
Yeah.
Because I will get an error, but I will not realize where is the point.
Yeah. Good point. Thanks. I think that's a good feedback. We should do some materials like that. Okay, so quick recap is that we need two things. We need something to give us a graph, and we need something to lower individual ops to the XLA subgraph, right? So here, this process is called lowering, and the word lowering just means implementing the semantics of one offset in terms of another offset. Here, the first offset is A10 ops. That's what PyTorch calls their ops. I think it stands for A tensor library. And you can actually do the lowering the other way. You can also write XLA ops in terms of A10 ops. That's also called lowering. It doesn't matter whether you just the offset feels higher level or lower level. It's just if you write one offset in terms of another, you get a compilation going on. And in case of Torch XLA, we have a lazy tensor for graph capture, and we have a C++ APIs XLA builder for lowering. And as we hinted on the Dynamo path, so Torch Dynamo actually provides yet another graph capturing mechanism. So in the future, we'll try to reuse that more and use less of it.
Is your plan always to use XLA builder for lowering?
There's few ways where you can get the lowering. XLA builder is only one of them, and yes, Torch JAX is another way to get lowering. And you can. We are also doing. There is somebody with a plan of making stable HLO builder where you don't create HLO, but you create stable HLO directly using MLIR's bindings. I think that one probably gonna be the one.
I think that is kind of our recommended way going forward. I think XLA builder is no longer.
Okay, good to know. Good to know. Yeah. So Kevin Gleason is he's working on stable HLO builder, and probably we're gonna go to his work. Yeah, that's great. And personally, I'm all for making compile time dependencies into runtime dependencies, so we can build separately, and we don't have to worry about like ABI issues and pin updates and version conflicts and all those things, which will help to do like stable stack and whatnot. Okay, I'll talk a little bit more on the new features of Torch XLA 2.7, not exhaustive, only the ones which I find interesting and I actually happen to know how it's implemented, so I'll talk about those. Here is a blog post on the pytorch.org. Feel free to read it. So one of the new features is called JAX, right? So what it does is that if you have a JAX function here, JAX function AB, normally you can only pass JAX arrays to JAX functions, right? So this call JAX operation allows you to call a JAX function using torch tensors, right? So here call JAX with the JAX function, and then the two torch tensors which are allocated here on TPU. It has to be XLA tensor though. And then you will call this JAX function on those two tensors, and then you get the result, right? So here we're doing another +2, and then we can get the stable HLO of my graph, and we can see here there's a call to a stable HLO function, and that stable HLO function is actually the one generated by JAX. Sign and dot general is the sign and maximal, right? How does that work? The way it works is because HLO has a op called call, and what that op does is calls a XLA graph, right? Arbitrary XLA computations, and then it doesn't care how that XLA computation come into life. And guess what? JAX can lower to HLO, right? So here's kind of like the puzzle. Those two features always existed since the very beginning. There's the ability to call arbitrary XLA computations existed since 2 years ago. This is akin to having like CFFI in Python or like inline assembly, right? Because torch XLA gonna run on HLO if we already have the HLO to say okay, run that, right? So that is a feature that already exists, and we just put the 2 and 2 together so that we can call to any JAX functions. We're not converting tensors to JAX and call the JAX function and convert the JAX array back into tensor. We're not doing that. Instead, we're getting the JAX function, convert that into HLO, and then just wire the emit the call operator in XLA to call that HLO, right? So that's what we're doing, and that's why we get this one graph.
You have device XLA there. Can you
Yes.
specify devices like accelerator or host?
No. So the way to get like SPMD sharding is that you first do device equals XLA, because PyTorch itself doesn't know about the sharding. Only XLA knows about sharding. So, but after you create the tensor, by the way, this is a lazy tensor. So this is lazy. It's not immediately materialized. You can do mark sharding on X. You will remember the sharding on X. So at the moment when you materialize it, either via computation or via printing or via weight, the graph we emit will have the XLA, like the SPMD shardings.
What do you mean sharding? Why?
There's an API called mark sharding, which takes a tensor and takes a sharding spec.
Yeah, I mean, I'm asking more like specifying whether the memory is living on the accelerator or the host, as far as like.
This goes to accelerator.
Right. Can you specify it?
You can do PGRT client equals blah, but then it will be for the whole program.
Right, but you can do host offloading today, where you can run an execution primarily on the accelerator and partially on the host.
Right now, we have host offloading of tensors, but not of computer.
Okay.
Yeah, so there's a custom call where you emit like host to device transfer, right? We have that custom call as a function that you can call, but it only works for. Yeah, we were only doing for like a host offloading, activation offloadings. We didn't do the host offloading on compute.
Just a follow-up question on that.
Yes.
So, because you're mixing up the torch and JAX code here.
Yes.
So for example, in the graph, and if I don't specify decorator at the rate on top of that JAX graph, how is the graph being stored? Is the graph being stored only as the forward, backward, same as PyTorch way?
So if you just do this and do call JAX, and you try to do backward, you actually don't get the backward, right? To get the backward, you actually need something else, which is I'll also cover that. Is that we have to wire the way for torch to declare a custom backward. Sorry, is to use this autogradle functions class, right? And you register forward and backward. So here, what we need to do is forward. You call the JAX function, but you also call VGP to get the VGP. You save the VGP, and then you backward. You call the return VGP, and then you get the backward, right? And we actually did that with another feature called assume pure, but that one is not in 2.7. It will be in 2.8. And actually, we'll kind of go through that a little bit as we go. Okay.
So just one part. So then, what is the recommended way? So because he also mentioned like you can put some computation on host and some computation on accelerator, for example.
Yeah.
So if I'm doing, let's say, data loading, should I keep most of my data formulation or like any kind of operation that I'm doing on data, that on the host, and then once I'm running the graph in a
Yes.
loop, should I keep that, or should I keep like old style, like TensorFlow lifestyle, TF records, or some sort of protocol buffer files different? So how best to optimize the entire pipeline?
Okay, good question. So for training,
Yeah.
when you load the data, you load to host.
Okay.
And then you move the data and then you run the graph.
Should the operations be, so if I have let's say PyTorch, some data operations, should I keep them on the host?
On the host, yeah.
Okay.
So so there's when we talk about host offloading, there's actually two host offloadings there. The one you hinted is the XLA host offloading, where the CPU operation is still another XLA graph, right? And then there's a PyTorch host offloading where you just do tensor.to CPU. You get a CPU tensor backed by PyTorch native. And if you do math on that CPU tensor, you actually get the PyTorch native behavior, the eager mode behavior, right? There's no XLA graphs whatsoever. Like it's PyTorch doing the math, not XLA doing the math. Those two are all valid, but I think for things like activation host loading while training, you don't want to cut the graph in the middle, and that's why we want to do the XLA one. But if you are doing things in the beginning, or like loading the data, or things in the end, like transforming the output of a diffusion model into the JPEG, right? So those things you actually do want to do on CPU, right? You do want to do it like tensor.to something CPU, and then do the work that way. Okay, so here's to show that this is the graph compiled by JAX, and here is emitting the call operator to call that graph. So here's a little quiz. If I add a print A here, what will you see printed on the terminal? Any guesses? Lazy tensor? That good guess. So what else? Any other guesses? Any other guesses? I'm adding a print inside of my JAX function, and then I'm calling this xb.callJAX with my JAX function. Yep. Okay, that's a pretty good answer. Yeah, so the answer is here. This is what you get printed. Trace the shaped array with dynamic Jasper trace. So if you are working with JAX, you're gonna be very familiar with this. This is what JAX uses to trace, right? So how we get implemented call JAX is exactly this, right? We have JAX func to XLA computation. How you make a JAX function into XLA computation? We have to do some tree flatten and tree unflatten stuff, because XLA computation is going to be expecting a flat list of inputs, so we have to match that. But inside of JAX func to XLA computation, as what you would expect, we're doing JAX jet, and then we're getting HLO proto out of the JAX jet. That's all. And sorry?
Even in the future release, you're hoping for eager mode on JAX.
Eager mode is not eager mode on JAX. It's eager mode on Torch. So eager mode is different. Yes. Yeah. So JAX can go to HLO by its own means. We don't care how it does it, but we say here's the JAX function, give me the XLO, and then after that we wrap it into computation. We call it.
This is a stable HLO computation graph.
It's actually HLO proto. Yeah, JAX can also go to stable HLO. So but because we're still using XLA builder, so now we ask JAX to give us HLO proto, and we call the HLO proto.
And this is fully optimized, so has it already gone through the entire XLA compiler passes?
That's before going to XLA pass. So after we get this graph, we give this graph to XLA compiler, to the PRT, and PRT will run and let's compile.
This is the graph.
This is the graph you're gonna get, right?
You get. So it's just stable HLO.
I printed as stable HLO, but inside is actually HLO. Yeah. When I print it, I do the conversion on the fly and then print it like this. Yeah. Okay, so sample applications. One of them is shard S. So this is a wrapper over JAX shard alike. And the reason to have it is, now that JAX have explicit shardings, maybe it's less useful. But we have this because if you are tracing and you are in inner node, you don't have the sharding. But if you want to say, I want this thing to be sharded the same way like that thing, there's no way for you to get the sharding and then apply the sharding. And we implemented this because right now in Torch AutoGrad, if you are SPMD mode, the gradient doesn't get a sharding. So XLA just make up a sharding for the gradient. But the ideal way to shard the gradient is the same way as your input, right? So we use shard S to tell XLA to say, hey, while you're computing the gradient, make the sharding the same as the input, right? So that they have the same sharding, they are in the same devices. Another application is assume pure, and this is a decorator where you put on top of a function to signify that this is a pure function and this function will not change, or all its values depend on input, right? So if the input don't change, your function don't change. And what we do inside is that we use Torch JAX to convert this function into a JAX function, and then we JAX it. And then we attach the AutoGrad with a forward-backward with the JAX's VGP, so you get the gradient. So with this, we don't need to trace again to find out if I'm still the same graph. You will just inspect the input. If the input shapes didn't change, you assume it's the same graph, you just launch the graph. It saves the tracing overhead. But it relies on the fact that the function has to be pure. So whoever's applying this decorator has to know what he's doing, right? If the function is not pure and you put assume pure there, you might have a numerical issue. It's no longer sound, but that's on the developer. And we did a bunch of improvements on developer experience. Before building PyTorch XLA from source is actually a lot of work, right? You have to get PyTorch, clone PyTorch XLA inside, and then build both from source, build a wheel so that there's a generated headers, and build a PyTorch XLA with the Basel and figure out which version of Basel works. Right now, we coded all those steps into this script. So now you can just do build developer. Dash B PyTorch if you want to rebuild PyTorch, and you don't do dash B PyTorch if you already did that before. You only need to build PyTorch XLA. And then we have this script. We added few Git hooks for you to sync all the submodules and auto format before you submit, so you don't hit the client format errors and stuff. We did a bunch of improvements on build time and CI runtime. So in the future, we'll keep doing that. We hope to get more contributors. Highlights on sister projects. That will be really fast. So we have two sister projects right now. One is Torch Prime, is the reference model implementation in Torch XLA. So we implement a bunch of models, we optimize them with SPMD, with the sharding, so that people can look to say, here are the benchmarks they're getting. It's on the GitHub as well to say, oh, what numbers I should expect and how to get those numbers, right? How do I shard? Which dimension I shard? What API to call? You can. It's meant as a reference, so people can look and learn how those models are implemented. In the future, we're adding Llama 4 and DeepSeek. If you want to reach out and chat with them, here are the emails for PM and engineering TLs working on this project. Next sister project is VLM. VLM uses Torch XLA to run on TPU. And it has pretty good performance, and it's very easy to set up, right? So the documentation is already live on the official website, and you can get the Docker, you can run the Docker, or you can use this command, VLM serve with the model you want to serve. You have it running on TPU, and we're actively optimizing it for V6E and the future versions, and Ironwood, which is the future version of TPU. And here are the contacts. Yaron is the TL, and Brittany Rockwell is the PM. And we have a bunch of future bets. Eager mode, improve the Torch compile, and then the UX, the future UX will be Eager plus compiled, meaning it's okay to mix and match. But of course, the more things you put on compile, the faster your thing gonna get, right? So we already chatted about this a bit. And since we're on time, we can probably stop here. Any questions? Questions? Yes.
I have a question. So, in the future, is Torch XLA going to be seamless? So, for instance, there make models today that work right on my Torch GPU, and then is it going to be like a simple click of the flag is going to just work?
Yes, that is the hope. So the only thing that we want people to change is the device. If you have device equals CUDA, you want to change the device equals XLA, that's all you have to do, right? Thanks.